Hi, in this video we're going to talk about implementation of MIPS32 pipelining using Verilog as my coding language and Cortex as my software. I have my MIPS32 pipelining block diagram right here, the schematic block diagram, and we're going to follow pretty much the same thing. We have our 5 stages of MIPS, starting from a fetch to decode to execution, memory, and then finally write back. Also, I have my two memories right here, RAM, which is near my main memory, and ROM, which is near my program counter. Also, this two blocks right in between of ID and execution and memory are my intermediate register blocks, and this is going to store the value of my ID and execution block temporary in them. So each and every Verilog file will consist of all the signals right here, which is exclusive to uh, the respective block, and we are defining each one of them. Let me give you a quick review on how we can create a new project in Quartus. You just go to File and then select New Project. I cannot show you right now because it's asking me to close my current one, but you get it. You go to Files, click New Project, give your project name, give your top module name, set up your coding language. You have like bunch of coding languages there. I've selected it to Verilog, and that's it. So here my project name is under MIPS_DH_INST01_jump, and my top module is MIPS32. You go to assignments and click settings, and under general you select your top level entity. I've selected mine to MIPS32. After defining each one of the blocks, you have to give your test bench. So my test bench file is right here and under the name MIPS32_test bench. And also you're going to set up this. So you go to assignments, click settings. Under EDA tool settings, you go to simulation. Then you check mark on compile test bench, and then click test benches right here. I've already set it up, and then this window is going to pop up. So you give your test bench name, you give your design instance name, which is DUT, and that's how you set up your test benches. Now let us take a look at a very simple assembly code that we're going to be executing using our design. So this is my assembly code which I want to execute. It's a very simple assembly code. As you can see, I have my 4 registers R1, R2, R3 and R4, which are first being initialized, R1 to 10, R2 to 6, R3 to 1 and R4 to 0. And then this block right here is where my loop is going to begin. So at the starting of my loop, my branch equal instruction is going to check if my R2 and R3 are equal. If they are equal, it's going to go to next loop, or else my value of R4 is going to get incremented by my R3 register, and my R3 is going to get incremented by 1, and it's going to go on and on and on. Also, we're going to check if the value of R4 at 150 must give us simulation time of 600 and 650 nanoseconds. So this is the condition that we're going to verify. We have our machine code of our each instruction right here, which we're going to be importing into our ROM file. Let us see how we can do it. So we first create a separate text file for it and import our machine codes right here. Then you save it, and then you go to your ROM file and you mention this Verilog inbuilt function known as readmemh. So readmemh is going to import all the text files into your Verilog files. So you give your readmemh function, and inside the bracket you mention the path of your text file. So that's how you define it. So my design is ready to is already compiled and my RTL is ready to view. Let us take a look at my RTL view. So you go to tools and then you click netlist viewers and then RTL view. So this is my RTL view right here. One thing you want to make sure is your RTL view must be kind of similar to the block diagram I've shown you before. It doesn't have to be same, but kind of similar. If you on the left hand side you can find your top level entity, which is MIPS32. If you click that, you can have your sub blocks right here, your sub files, and if you click each one of them, you can get more information about them. So that's it. I think my RTL looks pretty fine to me. Now let us go to simulation report. For simulation report, you just go to tools and then click run simulation tool and then RTL simulation. Then this is my wave diagram right here. These are my values for R1, R2, R3 and R4. So first our values are initialized correctly. My R1 is 10, R2 is 6, R3 is 1 and R4 is 0. So after the first loop, my R3 is supposed to be incremented by 1 and R4 by 1 by R3. So my after the first loop, my R4 is 1 because 0 plus because 0 plus 1 is 1, and my R3 is 2. Oh, what's happening? And then it's gonna go on and on and on. It's gonna get incremented on and on and on. Now let us go all the way down to check the value of R4. 78, 160, pretty close, 145, right here. So I have my R4 equal to 150 right here, and the simulation time for it is 6,650 nanoseconds, and that's what we wanted. Thank you so much for watching.